Wow. Got the attendance thing. Not the end of the world. Welcome, class. Oh, well, I say welcome. Class. Welcome. That's not what I wanted. Okay. Right. There's the attendance form again. Starting in just a second. All right, welcome to the last week of classes. Today we're talking about graphics and trig functions. What else? There's something else I want. There's something else on my mind. Oh, I totally forgot to bring the attendance form thing. Don't sweat it. It's not that big a deal. You can go fill it out later if you wanted to by going this. That'd be great. If you didn't, it wouldn't matter that much. It matters a little bit, not a lot. The other thing, I finished grading the exam. Most of the homework's been graded. We'll try and get that finished up this week. There was something else on my brain. Oh, I know what it is. I thought there was, but it's not there. I will post a link to sometime today to there's typically a quarterly evaluation that the students can fill out. So we have an evaluation, you can fill it out. I would like for you to fill it out. Do so when you have a chance. I'll make sure that link is there so you can access it easily. Bless you. Yeah, and I hope you all have a nice, lovely Thanksgiving. Good break to recharge and re-energize before the final push towards the end here. Yeah, let's talk about graphing some trigonometric functions, specifically sine and cosine. So things I want to use are sure. So graphing sine and cosine. When I think about graphing sine and cosine, I usually start with drawing a little unit circle. So I'm going to draw myself a little unit circle over here with the usual 4 points on the unit circle. where this angle here is 0 radians, and the point is 1, 0. And this angle up here is pi over 2 radians, and the point is 0, 1. And this point over here is going pi radians, and the point's -1, 0. Down here is 3 pi over 2 radians, and the point is 0, -1. And over here, this could also be 1 full revolution, which is 2 pi radians. Doing that is going to help me plot the points on my graph, because what we're going to do now is we're going to say that the x-axis is going to be the angle values and the y-axis is going to be the output value. So one thing to be aware of here is that the x and y that we're graphing here are not the same as the x and y coordinates that are on the unit circle. Right? So we're thinking of x as the angle and y as sine of that angle when we graph sine of x, or cosine when we do the cosine. So here, we don't usually need to make a table, but I'm going to make a table this one, well, maybe probably often, but typically I just look at the unit circle and be like, oh, if my angle is 0, sine of 0 is 0. We can make a little table as well. And my angle is pi over 2, sine of pi over 2 is equal to 1. So when I go to pi over 2, I'm going to go up to, let's say this is 1 high. So that's 1, that's -1. I do encourage you to label your axes in a way that is convenient for you. Sometimes it's nice to make the units whatever we want to be. So when my angle is pi over 2, the sine value is 1. When my angle is pi, sine of pi is 0. My angle is 3 pi over 2. Sine of 3 pi over 2 is equal to -1. Come on. And finally, 1 full period later, when my angle is 2 pi, sine of 2 pi is 0. So these 1, 2, 3, 4, 5 points that we typically plot on the sine graph and the cosine graph are kind of what I usually refer to as the important points of the graph. They break up the full period into 4 equal quarters. And each of these quarters kind of has the same shape. So we could do a little bit more if you wanted to. I typically don't. Like you might think if this angle here, this pen is doing something weird. If this angle here is pi over 6. Sine of pi over 6 is 1/2. So we can think about that point there being 1/2 as well. I don't usually plot that point when I'm graphing sine. I really only typically plot those 5 points. But here's what this first quarter looks like. Looks like that. We're getting a little bigger, and we get up to point 1. It's not like a straight shot, right? Because the sine values, if you think about on the unit circle, the sine values start off at 0. They get smaller, and then as we get this way, we kind of get smaller faster. And then it kind of just looks like this, but reoriented. So I'm going to kind of think about flipping this over, because in the second quadrant, we've got the same values. They're just going in the opposite order. In the third quadrant, the sine values become negative. In the fourth quadrant, they're also negative, but going back towards 0. And this is 1 full period of our sine function. One full period goes from 0 to 2 pi. And the reason we only graph a full period is because after that, it repeats, right? So if you kept going around the circle, you would just get the same values for sine, right? If we went to 5 pi over 2 and 3 pi and 7 pi over 2 and 4 pi, we would just get this whole graph translated 2 pi over to the right and also 2 pi over to the left. So typically when we're graphing trigonometric functions, we're usually only ever asked to graph a period or 2 because that kind of tells the entire story. A couple things to observe here. The most important thing I think is to observe the following. Each of these important points that I typically look for when I'm graphing sine, and I encourage students to look for when they're graphing sine or cosine, I'm gonna draw a layer here, is that each of these important points is exactly 1/4 of the entire period away from each other. So from 0 to pi over 2 is 1/4 of a full period. From pi over 2 to pi is 1/4 of a full period. from pi to 3 pi over 2 is 1/4 of a full period. And finally, from 3 pi over 2 to 2 pi is 1/4 of a full period. And when you think about it this way, a quarter plus a quarter plus a quarter plus a quarter is 4 quarters that gives you the whole entire period. So I really like to think about breaking up sine and cosine into 4 equal quarters. And as long as your period is the usual 1 revolution of the unit circle from 0 to 2 pi, you're really just breaking it up into the 4 quadrants. 0 to pi over 2 is quadrant 1, pi over 2 to pi is quadrant 2, pi to 3 pi over 2 is quadrant 3, 3 pi over 2 to 2 pi is quadrant 4. So that's a couple of the things I'm thinking about when I'm graphing this. Let's see, what else do I want to say here? Not a lot, I guess. I suppose I could say the following. Just good things to know about sine and cosine. The domain is everything. There are no domain restrictions. You can take sine or cosine of any value. The range, on the other hand, is very limited. The biggest sine can ever be is 1. The smallest is -1. This is an important fact you will use a lot next quarter, possibly. If you ever, when you start talking about the squeeze theorem or the sandwich theorem, this fact that sine of x is always less than or equal to 1 and bigger than or equal to -1, or cosine of x is always less than or equal to 1 and bigger than or equal to -1, is often used when you're using a squeeze theorem kind of thing. What else do I want to say? Yeah, let's just say that here. The period is generally 2 pi, although that can change. And the amplitude for these two functions is 1. The amplitude is just how high up and how far down we go. I typically think of it as the total length of the range divided by 2. So our range here goes from -1 to 1, which is a length of 2. If you divide that by 2, you get 1. There's other ways of seeing it as well, which we'll see on the next page, but that's really how I like to think of it, is how long the range is divided by 2. All right, let's graph cosine as well. For cosine, we're going to do the same thing. We're going to look back at our unit circle, but instead of using the y values to get sine, we're going to use the x values to get cosine. So when I see cosine of 0, I'm going to get the value of 1. And cosine of pi over 2, the value is going to be 0. And cosine of pi, the value is going to be -1. And cosine of 3 pi over 2, the value is going to be 0. And cosine of 2 pi, we're back to 1. If you've gone a full period, you should always end up at the same y value that you started at. The same height, I should say. And then the graph is really going to look almost exactly the same, if I can graph it well. It does have this smooth kind of wave shape. It's actually called a sinusoidal function. That's the official name for it. Sine and cosine look the same. They look like each other, except one is shifted, the other one, they're just shifts of each other. If I shift this whole entire graph of cosine, pi over 2 to the right, it would look exactly like sine. Or if I shifted all of sine, pi over 2 to the left, it would look exactly like cosine. So they're very, very similar functions of each other. They're just transformations of each other. But they do offer different things, so we graph them both. There's not a whole lot to say about cosine that we haven't already said about sine. It's got the same domain, same range, the same period, same amplitude. And all of the important points that I think about are also a quarter of a period away from each other. Something else that was crossing my mind when I was saying this. You should try your best when graphing these to get this shape. It shouldn't be too straight. It shouldn't be too pointy. It should be nice and curved. Oh, I know what I was gonna say. It should be relatively smooth. And when you approach the highest points, let me grab another piece of paper here real quick, just kind of make it easy. Yeah. So like if I was graphing sine or cosine, and I had made my little graphing it kind of freehand, up to 1, down to -1, over 2 pi. Typically what I do is I cut each of those in half, and then cut each of those in half to get my 4 quarters. So I take my whole period, cut it in half, cut each of those in half. What I want to point out, if I'm graphing, say, sine of x, so I'm starting here, and then I'm going high, and then back here, and then low, and then back here. What you want to be careful about is when you approach this top point here, you don't want to overshoot it. it's really easy to kind of go at that and be like, oh yeah, oh no, too high. So you want to make sure you're starting to level out when you get there. So you're topping out when you graph that point. And then same deal this way. You come down this way and you bottom out right there. Doesn't have to be perfect. It just has to be decent. Yeah. Sorry. So anything else to say here? There was one other thing to say. No, I guess we're good. All right. So let's talk a little more generally. Sine and cosine typically have this shape. Oh, I know what else I was going to say. The other thing I typically think about when you're plotting these points is I kind of think about the ones that are at the top as the high points and the ones at the bottom, the low, and the other ones at the middle. And so whenever you're graphing sine or cosine, there's always kind of this push and pull where you're hitting the top and then the middle, and then the bottom and the middle. It's always away from the middle, back to the middle, away from the middle, back to the middle. So I think about this one as middle, top, middle, bottom, middle, top, middle, bottom, middle, top, middle, right? It's just the same pattern every time. Top, middle, bottom, middle, top, middle, bottom, middle. You keep going back to the middle, back to the top, back to the middle, back to the bottom. It's a little repetitive, but it's what my brain has started to think of when I do this. So I usually think of sine as starting at the middle and then going top, middle, bottom, middle, whereas cosine starts at the top and goes middle, bottom, middle, top. There's lots of different ways to think about it. I really think this is the best way to do it, though, is drawing a little unit circle here and just saying, oh yeah, I'm using the y values for sine, the x values for cosine. So let's get a little more interesting. Let's talk about how we can change this up a little bit. So we can use our usual techniques for dealing with transformations. There's a lot of things we're going to transform. Specifically, we're going to start with talking about the amplitude and the period. So this number out here, A, is the amplitude. Well, it's usually the amplitude. I should say, really, the absolute value of A is the amplitude. In other words, the amplitude has to be positive. So if you had like a -3 times sine of x, we would still say the amplitude is +3. Let's talk about what D is going to be here. D is just a vertical shift. C is just a horizontal shift, also called a phase shift. I don't know why we specifically, well, that's not true. The reason we probably specifically use that language is because we think of sine and cosine having kind of a phase as opposed to just a horizontal shift. So a horizontal shift, also called a phase shift. And finally, probably the most important of these transformations is the horizontal compression or stretch. So that's going to be a horizontal compression or stretch. Which is really going to affect the period. So if we stretch out the function, we are making the period longer. And if we compress the function, we're making the period shorter. And there's actually a very straightforward way of finding the period. The period is always going to equal 2 pi divided by whatever that coefficient is. And we'll talk more about that in the next example, or the example after this, because it's kind of easier to see the example. But typically, if we're trying to find the period, it's just 2 pi divided by the coefficient of x. That's it. Yeah, I suppose we already wrote this down. I don't think, yeah, I know about amplitude, the previous function. So our parent functions had an amplitude of 1. I saw the coolest thing the other. Sorry, I just had like, you know how like I opened the door and like the door stopper like moves around. I saw a really cool door stopper the other day where it had like a little kickstand on it, so you could like pop it up and it would just close. It was like I know it's totally off topic, but like it was like I feel like we should get them installed here because I happen to struggle putting the thing in there. It doesn't always stay very well, but like had like a little thing that went down and then you could like pop it back up and then just go back up. Anyway, sorry, I got a little distracted. I saw the door and I was like, oh, that's neat. Back to math. As far as the period goes, same deal. Our parent functions have a period of 2 pi. I got ahead of myself, I guess, but I suppose I should write it here. Great. So if we're going to graph something like y equal to 3 sine of x, the only thing that's changing from the parent function is the amplitude. So here, the period is still 2 pi. Or if you want to think of it, it's 2 pi divided by 1, because the coefficient of x is 1. And the amplitude is equal to the absolute value of 3, which I know is just 3. But it is good to get into the habit of saying, I don't want a negative amplitude. It should always be a positive amplitude. What's going to happen here is this is just going to stretch the function 3 away from the x-axis. So in our previous graphing of sine, we had the following points. And again, I don't think you need to make these tables, but I like making them to kind of show what's happening. So previously, we graphed our usual nice angles: 0, pi over 2, pi, 3 pi over 2, and 2 pi. Those were the usual inputs if we don't change the period. We're just breaking up the period into 4 equal quarters. And then our sine of x was our typical 0, 1, 0, negative 1, 0. And if we're going to take 3 times sine of x, all we're going to do is 3 times each of these values. We're going to get 0, 3 times 1, 3 times 0, 3 times negative 1, 3 times 0. I don't think you need to make this table. I think all we need to do is look at the unit circle, be like, okay, 1, 0, 0, 1, negative 1, 0, 0, negative 1, and say, okay, well, sine would have been 0, but I'm multiplying it by 3. So I'm going to get 0. And label this so we know what we've got. And sine of pi over 2 would have been 1, but we're multiplying it by 3. And sine of pi would have been 0, but we're multiplying it by 3. And sine of 3 pi over 2, we're multiplying by 3. Sorry, we're multiplying negative 1 by 3. And then sine of 2 pi is 0, and 3 times 0 is 0. We're stretching out the sine function. But it's still got the same general shape. So this is y equal to 3 times sine of x. Versus, just for comparison, here's the parent function. I'll graph it dashed. We're just stretching it away from the x-axis by a factor of 3. Notice, just because I think it's worth noticing, if you take the total length of the range, so the range here goes as low as negative 3 and as high as 3, the length of the range is 6. And 6 divided by 2 is 3, which is your amplitude. That's another way to think about it. Okay. So the rest is just graphing sine and cosine. That's all we're doing is just graphing more sine and cosine. I know it's not super exciting, but it is so these are graphs you will see about of all the trig functions you will encounter in the rest of your math career. Sine and cosine are the ones that come up the most. Yeah, we'll talk about tangents a little bit, and well, maybe. But secant, like tangent, cotangent, secant, cosecant are graphs that you might encounter, but they are less important than sine and cosine. So let's talk about changing up the period. This is where we're going to be a little bit more careful here. So let's say we want to graph y equal to cosine of 4x plus 1. So notably, the plus 1 is going to shift it up by 1. And the 4 there is going to change the period. So that 4 is going to modify the period. So it's going to make the period longer or shorter than it would than the natural period of 2 pi. I think I heard someone say shorter. I'm gonna go with that. The period now is going to be 2 pi divided by that coefficient of x, which is 4, which is going to be pi over 2. So in this example, the whole entire cosine graph starts at the top, goes down to the middle, down to the bottom, back to the middle, back to the top, is going to happen in a length of 0 to pi over 2. Here's why that's true. And I think this next part is actually kind of maybe the most interesting point here. The reason this happens is because, well, to get a full period, you have to make one full revolution of the circle. You have to get cosine having all the positive values, then cosine becomes negative, then it becomes negative again, then it goes back to being positive, and you end up where you started. At least that's for cosine, right? For cosine, right? We start positive, we go negative in quadrant 2, negative in quadrant 3, positive back in quadrant 4, and then we do it all again. Quadrant 5 is the same as quadrant 1, right? You've gone all the way around. So the whole idea is that we need to make a full revolution or a full journey through the angles from 0 to 2 pi or 0 to 360 degrees. So here's what's happening. Our angle now isn't x. Our angle is the thing we're taking cosine of, which is 4x. So what we need is for our angle to go from 0 to 2 pi. What that ends up meaning for us is that, well, if we divide everything by 4 here, and isolate x, and 0 divided by 4 less than or equal to 4x divided by 4 less than or equal to 2 pi divided by 4 becomes 0 less than or equal to x less than or equal to 2 pi over 4, which reduces to pi over 2. So that's really why we do that division by the coefficient of x to get the new period. Is because we're saying, oh, well, if x goes from 0 to pi over 2, then 4 times x will get us all the way from 0 to 2 pi, which is a full period of the function. So now we're going to find the same 5 important points, but they're going to be all smooshed in to this much, much smaller interval. So how do I find my 5 important points? Well, there's a couple ways to go about it. Here's what I recommend. Start at the beginning. Which unless you have a phase shift is going to be 0. So our first important point, and let's see, how do I want to label this? I've gone back and forth between my labeling. Yeah, let's just stay. My first important point I'm going to call x sub 1 is 0. Starting at 0. And like we were saying before, each of the points that we want are a quarter of a period away from each other. Right? And all the other ones, I know all of them have been the same period, but each of these have been exactly pi over 2, pi over 2, pi over 2, pi over 2, so that was a quarter of a period. Well, now our period has changed. Our period here is pi over 2. And 1/4 of our period is going to equal 1/4 times pi over 2, or 1/4 of pi over 2, which is pi over 8. What we're going to do to find all the other important places where we're going to get important points is to just keep adding a quarter of a period. So our next important spot is going to be our previous spot plus a quarter of a period, which is going to give us pi over 8. And our next important spot, the third important point, is going to be, well, we're just going to go another quarter of a period. In fact, let me start graphing it here. So I know it's going to be a little bit, a lot here. Let's see. Yeah, okay, let's say that's 1. That's -1. So cosine, yeah, sure. That's 2, -2. So normally I would start at a height of 1 for cosine, and then you down to the middle, down to the bottom. Because cosine, right, if we unit circle it, cosine starts at 1. But we're adding 1. So when I do a vertical shift, what I like to do is draw what I call a new middle line. Not a horizontal asymptote, although it's going to kind of look like one. I like to draw a dashed line at whatever my new vertical shift is. So I've shifted the whole graph up 1. So the new middle is 1 higher than it was before. Okay, so now cosine starts 1 above that. And then the next point is at pi over 8. So I'm cutting this in half. this full period here in half and then in half again, which is kind of gross. But there's our points. There's pi over 8. So cosine, we're starting up at the top and then going to the middle. And then the next point we're going to look at, well, I'm going to take pi over 8 and I'm going to add another quarter of a period, which is pi over 8, to get 2 pi over 8, which I actually probably wouldn't reduce. I would probably just leave it as 2 pi over 8 because I'm going to have to add pi over 8 to it again anyway. So the second point here is 2 pi over 8. And each of these is a quarter of a period away from each other. That's 1/4 of a period. That's another quarter. We're going to get another quarter and another quarter. Zoom in a little bit. So just like the previous cosines, we're starting at the top, then going to the middle, then going to the bottom. How do I know that's the bottom? What's my amplitude? What is my amplitude? Well, it's the coefficient out here that we don't write, which is 1. So if there isn't a coefficient in front of cosine or sine, the amplitude is 1. Just like the general parent function, the amplitude is going to be 1 unless we change it. So our amplitude's 1, meaning we're starting 1 above and going 1 below. So then we get the next important point by adding another quarter of a period to our previous important point. So 2 pi over 8 plus pi over 8 is 3 pi over 8, which is right here. So cosine, top, middle, bottom, back to the middle. And then finally, the last point where we're going to end up where we started, we'll take your previous point, add another quarter of a period, and we're going to get 4 pi over 8. And I could leave it like that, but I'm going to reduce it just to see that we really end where we think we should end. 4 pi over 8 is pi over 2. So we've gone 1 full period, right? Because the period is pi over 2. We started at 0, we ended at pi over 2. And what we're doing is we're breaking it up into 4 equal quarters of that period. Now this one definitely is going to look very kind of smushed in because it is, right? We've got a lot less horizontal space to work with. It's still going to have the same sort of shape though. It's going to do that. And I do like to kind of draw little arrows that indicate that it keeps going on, right? It doesn't just stop when you draw 1 full period. It keeps going either to the left or the right. But that's 1 period of this much, much shorter function. So it's been shifted up 1. So instead of going as low as -1 and as high as 1, it's going as low as 0 and as high as 2. And it's been smushed into a period of pi over 2. We can still see that the total range here has a length of 2. So the amplitude's half that, which is a length of 1. Our range here, just to note it, is from 0 to 2 instead of from -1 to 1. Questions about any of this so far? Like specifically this example, are there questions that I can address? Typically, what I'm looking for when I'm graphing sine or cosine is finding these 5 points, specifically finding the 5 x values and then the appropriate top, middle, bottom values for sine and cosine. So when I was thinking about the cosine values here, I wasn't really thinking it was going to be like 1, 0, -1, 1, 0, -1, 0, 1. Although I was thinking about those, I was thinking about the unit circle and saying, okay, typically cosine, top, middle, bottom, middle, top, and then I shifted those all up 1. That's what I was thinking about when I was doing that. You could also make a table. I don't want you to have to do that because it's time consuming, but if you want to do that, it's totally fine. You can make a table and then add one to each of the values. So you could think of, no, I don't want, it's going to get messy if I do that. Okay, let's look at the next example, which is a little less messy. 3 cosine of 1/2 x minus 1. All right, let's write down all the things. So there's a couple easy things to see. Our amplitude is 3. You could say it's the absolute value of 3, but let's just say it's 3. Our vertical shift is going to be down 1. And our period is going to be 2 pi divided by 1/2, which is the same as 2 pi times 2/1, which is 4 pi. Okay. So although we're going to deal with the x values in a second here, let's think about the vertical shift for just one moment. Let's label these. Let's go with the standard 1, 2, 3, 4, -1, -2, -3, -4. So we're going down 1. So our new middle is at -1. I'm thinking of right there. You don't have to draw this new middle line, especially if you've got like a grid like this. I just like to draw it. It's helpful to me. And then our amplitude is how much? 3. That means we're going to be going 3 above and 3 below. So really, all we really actually care about is this value of -1, 3 above it, which is 2, and 3 below it, which is -4. These are where our highs and our lows and our middles are going to be. So we're expecting to start high because it's cosine, and then go to the middle, and then go to the bottom, and then go back to the middle, and then go back to the top. We just have to figure out what the x values are that are going to get us there. So our period is 4 pi. And whenever you're finding a quarter of the period, it should be less. So I've definitely seen people accidentally do the thing where they multiplied wrong and made it like 4 times as much instead of a fourth as big. So make sure that when you're finding the quarter of the period, which is going to be 1/4 times your period, make sure that that number is less than what you started with. 1/4 times 4 pi, the 4's cancel, and you just get pi. So 1/4 of our period is pi. We still don't have any horizontal or phase shifting, so our first important point is just 0. And then to find the next one, we're just going to take our previous one. Oh, I know what I should do. I'm going to write that. Yeah, fine. And write that as 0 plus 1/4 of our period, which is pi. And then to find the next one, I'm going to do something slightly different here, but it's going to be still the same. It's just going to be the previous point plus 1/4 of our period, which is pi plus pi, which is 2 pi. I know these are very easy to find for this particular example. It's still good to see the work. Our next point is going to be the previous point x sub 3 plus another 1/4 of our period, which is going to be 2 pi plus pi, which is 3 pi. And finally, our last important point, the end of our period, should be 4 pi. Well, let's check. It's our previous point plus another 1/4 of our period, which is 3 pi plus pi, which is 4 pi. I want to stress each time to get the next point, we're just adding 1/4 of your period to get to the next important point. We did up here as well. We added, right? Each of these were just adding 1/4 of your period. Okay, so cosine starts high, right? We know that cosine of 0 is equal to 1. So if I start at an angle of 0, cosine of 0 is 1. 3 times 1 is 3. 3 minus 1 is 2. We're starting here. The next important angle is pi. That's our next spot. And we're going to go down to the middle, which is not on the x-axis. It's at the middle line. And then at our next important point, which is 2 pi, we're going to go down to the bottom, which is -4. And then we're going to go at 3 pi back to the middle. And at 4 pi back to the top. And then we try to draw the best graph we can. Sometimes it's more challenging than others. Oops, like this time. That's pretty okay. I would also encourage you to look at Desmos to see a perfect version of how the graph looks. You can definitely get a better idea of the exact shape. This is a pretty, this is not bad. Pretty good facsimile of how sine or cosine should look. But if you want a precise, nice looking thing, you can look there to kind of see how it should look. That's not to say that your graphs have to be perfect. They should look somewhat like what we're shooting for. All right. More examples. We got time. So let's graph. Why are they all cosine? They're all cosine. We'll do another. We'll do a sine one too. The -4 cosine of 2x. So our amplitude is the absolute value of -4, which is 4. There is no vertical shift. We're not going up or down. And our period here is 2 pi divided by, in this case, 2. Now, let's make it very clear. That's the 2 that we're dividing by, which ends up being pi. So in the past, when we've multiplied by a negative in front of a function, what has that done to the function? Yeah, which way? Flipped it right this way, across the x-axis. So this is going to give us a vertical flip. So instead of, in the previous example, is cosine going top, middle, bottom, middle, top, it's going to do the reverse and start at the bottom and then go to the middle and then to the top and then to the bottom. It's the middle and then back to the bottom. All right, let's find our important values. So our first value is going to be, oh, I didn't find a quarter of my period. 1/4 of my period is equal to 1/4 times pi, which is just pi over 4. My first spot is still going to be 0. My second spot is going to be 0 plus the previous spot, which is 0. Sorry, oops, not 0 plus the previous spot. Sorry, that's a mistake. Not 0 plus the previous spot. It's the previous spot plus 1/4 of my period, which is 0 plus pi over 4, which is pi over 4. You do not need to be writing out so many pluses. Like you could just, I imagine most of you can be like, oh, I know 0 plus pi over 4 is pi over 4. I know pi over 4 plus pi over 4 is 2 pi over 4. Right? You could probably just write down that x sub 3 is 2 pi over 4 instead of showing all the work. I'm showing all the work to be expository. So I'm taking my previous point, adding another 1/4 of my period, and getting pi over 4 plus pi over 4, which is 2 pi over 4. And then I'm taking my previous point, adding 1/4 of my period, which is going to be 2 pi over 4 plus 3 plus pi over 4 to give me 3 pi over 4. And then finally, to get my last point, my fifth point, taking my previous point, adding 1/4 of my period, and getting 3 pi over 4 plus pi over 4, which is 4 pi over 4, which is pi. It is good to check, or at least mentally think about, is the difference between my starting point and my ending point the length of the period? It should be. And yeah, from 0 to pi, the length is pi, so that which is my period length. Okay, so I've got my important points here. I've got pi over 4 being halfway between 0 and pi over 2. And 3 pi over 4 being halfway between pi over 2 and pi. And then, let's see, we're going 1, 2, 3, 4, -1, -2, -3, -4. How much time do we got? Yeah, we got time. I'm going to make a table here just to show something. So you could just do the usual thing, except flip it over. But here's kind of why we're picking these specific x values. What we're doing, and I'm going to ignore the -4 part here for a second. Our angle or angles were 0, pi/4, pi/2, 3 pi/4, and pi. And I reduced the 2 pi/4 to pi/2. And then if we multiply each of those by 2, 2 times 0 is 0. And 2 times pi/4 is 2 pi/4, which is pi/2. And 2 times pi/2 is just pi. And 2 times 3 pi/4 is 3 pi/2. And 2 times pi is 2 times pi. Just 2 pi. Those are exactly the angles that we started with when we were just graphing sine and cosine. That's the whole point. That's why we're finding these 5 important values here, because when we multiply them by whatever they're actually being multiplied by here, you get back the original 0, pi/2, pi, 3 pi/2, and 2 pi. And then we know that cosine of 2x is 1. And cosine of 0 is 1. And cosine of pi/2 is 0. And cosine of pi is -1. And cosine of 3 pi/2 is 0. And cosine of 2 pi is 1. So that's why we're using these angles to get us these angles to get us these values, which we would then, if I made more room on my table here, I guess I'll draw over here, sorry. If we then did -4 times cosine of 2x, we're exactly getting -4, 0, +4, 0, and -4. So we're plotting these x values, these angles, against these y values, these outputs. So we're getting 0, -4, pi/4, 0, pi/2, 4, 3 pi/4, 0, and pi, -4. And again, I don't think you need to do all this tabling, but that's what's happening. That's what we're finding these 5 values, because they're the ones that give us the nice top, middle, and bottom values for your sine or cosine function. And then we do our best to draw. So instead of doing the usual cosine thing, it's flipped over. So it's going to kind of do this. So this is the bottom. And we're going to go up, 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 up. Done better. So there we go. There's your -4 cosine of 2x. Oh, it's all right. Interesting fact. If you're graphing cosine of 2x, you get 2 full periods in the usual period length. So if we drew this again, we would get another full period from pi to 2 pi, and you use exactly 2 full periods from 0 to 2 pi. And if you're graphing something like sine of 3x, you could get 3 full periods from 0 to 2 pi. It's kind of neat. So whatever the multiple of x is, that's how many periods you would get from 0 to 2 pi. Sometimes it's not very helpful, because it's like if it's sine of 2/3 x, knowing that you get 2/3 of a full period from 0 to 2 pi is not super duper useful. Yeah, we've got enough time. Let's do one more example. Speaking of 2/3. So typically, but certainly some of the time, you're not always going to have the whole kind of graph with nice markings on. You just have to draw it yourself. So let's say I wanted to graph y equal to sine of 2/3 x plus 1. Okay. The same sort of deal. The amplitude here is 1. You see that? Yeah. The vertical shift is up 1. Those are usually kind of the easier parts. So when I think about starting to graph this, I'm already thinking, okay, I know I'm going to go up 1. So my new middle, as I like to call it, is going to be 1. And then I feel like let's change the problem just slightly, because we can. It's not hard to do. Let's make the amplitude 2. just because it's a little more interesting graphically. I know it's terrible to change the problem midway, but I feel like it kind of time is all right. So the amplitude being 2 means we're going to end up going 2 above and 2 below. And really, those y values, 3, 1, and -1, are the only ones I care about. They're probably the only ones I would actually even write on my graph. So I know sine's going to do this whole starting at the middle thing and then going top and the middle. And I know it's been a while since we graphed sine, right? It's been all cosine for some reason. Let's find our period. And it's going to be 2 pi divided by 2/3. And again, that 2/3 is just coming from the coefficient of x right there. Do be careful. It's that coefficient of x, not this other. Oops, sorry, you can't see that. Apologies. It's that coefficient of x is not the thing that's out here in front. So it's always whatever is actually multiplying by x in your trig function that is going to help you find the period. All right, that's going to be 2 pi times the reciprocal, which is 3/2. 2 pi times 3/2 is 6 pi over 2, which is just 3 pi. So our period is 3 pi. And the quarter of my period is equal to 1/4 times 3 pi, which is just 3 pi over 4. All right, we're going to do this quick because we only got 2 minutes. Our first point is 0. Again, or I should say our first angle is 0. We still have a phase shift, so we're still just starting at 0. Our next important point is 3 pi over 4. We're just adding 3 pi over 4 to 0. I could do it this way. I always forget this. I'm just adding 3 pi over 4. It's going to add another 3 pi over 4 to get 6 pi over 4. I really do recommend not reducing your fractions because you're always going to be adding the same thing. So if you have the right denominator, adding that fraction with the same denominator is going to be easy. X4, we're going to add another 3 pi over 4. And 3 pi over 4 plus 6 pi over 4 is 9 pi over 4. And finally, one more time, I'm going to add 3 pi over 4, and I'm going to get 12 pi over 4. And 12 pi over 4 does reduce to 3 pi, which is good to check. Okay, so for the spacing here, spacing is always a challenge. I try, it's not a requirement. I try to make it so that x and y are generally have the same sort of interval length, meaning like I don't want my x-axis to be widely out of scale to my y-axis, but they don't have to be perfect. I know pi is about 3. It's not exactly 3. It's like 3.14, but I just say, okay, pi is about 3. So if I'm going to a whole 3 pi, that means I should be going out to like 9. Maybe it's probably not perfect. That's okay. Let's say that's the end right there. I know. So then we're going to take our period and cut it in half, cut each of those in half. That's how I like to find my 4 places on the x-axis. And then that's going to be 3 pi over 4, 6 pi over 4, 9 pi over 4. Sine starts at the middle. The sine of 0 is 0. And sine of 0 times 2 plus 1 is 0 plus 1, which is 1. And then we go up to the top. And then back to the middle. And then down to the bottom. Now be careful. A lot of people, when they go down to the bottom, they really want to like hit the x-axis. There's no reason to hit the x-axis. I mean, we're going to cross the x-axis, but there's no reason that the x-axis is important here. We're going to go down right there. And then finally back up to the middle. So here is our sine function. Oh, oops. It's all right. Again, one more time for references. You're welcome to pack up. That's one point again, right? 1/4 of a period. That's always the kind of important thing we are looking at here. Each of these are 1/4 of a period away from each other. You get 4 whole quarters, which is 1 whole period. All right. On Wednesday, we'll talk more about some graphing stuff and solving some trig equations. Have a lovely rest of your day. Here's the again. If you have the opportunity to do fill out the attendance form when you have a second later on today sometime. If you don't, again, not a huge deal, but if you could, I'd appreciate it.